I'm sure you must be aware of convolution neural network for image classification. But do you know a new novel architecture called Swin Transformer that can be used for image classification tasks, and Swin Transformers can outperform convolution neural network. In this video, we will understand what is Swin Transformer and implement it on MNIST digit dataset. So let's get started. First, if you go to Google and write Swin Transformer architecture, you'll see that it is a hierarchical vision transformer that utilizes shifted windows to enable efficient and scalable processing of images. There is a paper called Swin Transformer Hierarchical Vision Transformers Using Shifted Windows by people at Microsoft, and you can read more about the architecture and the functionalities and the way this Swin Transformer works in this paper. Basically, this is the architecture. For our help, there is a Python package called TIMM. This package can be used to create a Swin Transformer model for vision task. Now let's look into the code section itself. First, I'll import few libraries: Torch, Torch Vision. I'll import dataset and transforms, and from Torch utils I'll import data loader. The second thing I'll create is a transform, because every image will need a transform. Since I'm using a model that utilizes 224 by 224 image size, I'll use resize. I'll make 3 channel of each image, then transform it to a tensor and then normalize it. I will download the train and test MNIST dataset, and I'll create train and test loaders from that. Then I'll check if I have a device available or not. If not, I'll use CPU, but in my case I have a GPU. Then using team.create model, I'll create a plain model. I'll download the pre-trained weights, and I'll say that I have 10 classes since we are working with MNIST digit dataset. Finally, I will move the model to device. Then I'll create a criteria for the model and then an optimizer. I'll start the training loop. This training loop is running for 5 epochs. What I am doing is extracting the images and labels. Then I'll put the optimizer to 0 grad. Then I'll get the outputs from the model, create the loss, move the loss backwards and make optimizer take 1 step. I'll calculate the running loss, correct and total. Finally, I'll just calculate training loss and accuracy and print that for every step. As you can see here, the training process is finished and it took around 12 minutes, and you can see the accuracy is 0.98. So what I'll do is that I'll test the model against the test dataset. You can see that was pretty quick, and the training accuracy is about 98%. Then I will move ahead and save the model. Then I will recreate the model, load the existing model's weight and put it into evaluation mode, and then finally move it to the device. Then I'll write a predict image function. This will take image path and device, and it will return the label and the confidence. Then I have a separate test images and I'll check the model's performance on that image, and you can see it worked well. So this new architecture Swin Transformer seems to be working well on MNIST dataset, and if I would have run that for a couple of more epochs, the accuracy would be better as well. The code I have used in this video is available on my GitHub, and you can get it from the link in the description. I hope this video clearly explains how to implement Swin Transformer architecture for your use case. If you face any issues running the code I have explained, please get back to me in the comment section. I'll surely try to answer your queries. Finally, if you like the work I put on my YouTube channel, consider subscribing it. That helps. Thank you for watching. Enjoy the life, feel the music. Peace.